mobile.
Yeah, thank you. Good morning. So, we have one more day to go. This is getting closer. But today, in the morning, I am going to talk about the first topic is physical properties and characterization. So, it's in general it will cover magnetic phase, the ferroelectric phase, and most of the measurement techniques for magnetoelectric coupling we have looked at it already. So, I will just breeze through it, but I will mainly focus only on specific properties of ferromagnets and ferroelectrics. So, I am pretty sure most of you are familiar with ferromagnetic order, where there is spontaneous magnetization because of parallel alignment of atomic moments. And so, overall, below the Curie temperature, there is a finite magnetization. Above the Curie temperature, because of the thermal energy, there is random ordering of the moments. So, the spontaneous moment goes to 0. So, ferromagnet is very similar to ferromagnetism, but there are two kinds of magnetic moments. They are aligned antiparallel to each other, but they are not equal. So, that would mean that there is a net magnetic moment. So, the system behaves very much like a ferromagnet. So, the ferromagnetic ordering, those materials are generally called ferrites. So, ferrite would mean the ordering is ferromagnetic, but people kind of misuse the term because they call it bismuth ferrite, but it is not a ferrite. It is antiferromagnetic or very weakly ferromagnetic. So, you have to be careful when you call something a ferrite. Ferrite implies ferromagnetic ordering. Then you are also familiar with antiferromagnets, where there are two moments equal and opposite. So, the net moment is 0, and there are many materials that are antiferromagnetic. Manganese oxide, MnO, nickel oxide, cobalt oxide, iron oxide, they are all antiferromagnetic. Then the other kind is canted antiferromagnet. So, the arrangement is antiferromagnetic, but there is a net angle between the two moments, that is canted structure. There is also helical spin ordering. If you imagine a helix, the spins, the neighboring spins, they are making a certain angle like a cone. So, the helical spin ordering is very much like what is shown in this figure. So, the ferromagnetism, it's spontaneous magnetization, and it's arises because of ordered spin state in a magnetic material in the absence of any external field. So, it happens below a certain critical temperature, which we know it is Curie temperature. So, when heated above the Curie temperature, it becomes paramagnetic. So, the magnetic moments are strongly coupled through exchange interaction. So, anything that happens in one spin, it will be transmitted to the neighboring spin. So, it is collective excitation. The whole system behaves like what we call spin waves or magnons. These are bosons. They have very small energy on the order of milli-electron volt. So, the temperature dependence of the magnetization is given by this equation here. That is true only when you are far away from the Curie temperature. So, there is a 3^2 exponent in the way the magnetization decreases with temperature. But the one at the top, that equation fails when you are close to the Curie temperature, and very close to the Curie temperature, the magnetization will vary like what is shown here. Beta is called the critical exponent. It ranges, it is less than 1 certainly, anywhere between 0.3 to 0.5 depending on the material. But if you want to find the Curie temperature for a ferromagnet, strictly speaking, it should be done under 0 external field. If you apply an external magnetic field, there will be a spread in the Curie temperature. That is what is shown here. Now, these curves are shown for a series of fields 1 kGauss, 6 and 12, and as you increase the field, there is some error in the Curie temperature that is very evident from the way the magnetization varies with temperature for these 3 cases. So, how do you measure the magnetization? There are many ways to do that, and I will just quickly go through some of them. Vibrating sample magnetometer is commonly used, and this is what I have in my lab, the Faraday susceptibility balance, and there is also what is called an AC gradient magnetometer, and this figure shows a typical VSM, and the one on the right is the power supply and all the electronics for the system. And what is shown on the left is an electromagnet that will apply a magnetic field to measure the magnetization as a function of the static magnetic field. So, what you see here is a sample holder that keeps the sample between the 2 pole pieces, and then this is the vibrating unit, and the sample is attached at the bottom of this. These 4 coils are just copper winding placed very close to the sample. It can be mounted on the pole pieces or away from it, it does not matter. So, when you vibrate the sample has a magnetization and there is a magnetic flux. So, the flux will change as a function of time. So, from the Faraday law, you can estimate that there is an induced voltage in these 4 pickup coils, and that is given by the time derivative of the magnetic flux associated with the sample. So, you can use a standard such as nickel and do some calibration, and then for unknown sample just put it in, and then you can find the magnetization versus static field, and this can be done as a function of temperature or anything else that you want. And the Faraday magnetometer, it is as sensitive or even better than the VSM. What's here is an electromagnet with a tapered pole piece. The purpose of this is the field configuration produced by this magnet in such a way that there is a gradient in the magnetic field in the vertical direction. So, if there is a gradient, then there is a force on the sample. So, this force will pull the sample down, and there is a control electronics with a photo detector. So, when the sample moves down because of this magnetic force, it allows more light to go into the system. There is a photosensitive detection that will sense the deflection of the sample then it will send a signal to correct for that. So, ultimately what we get is the unit produces an output which is proportional to this force, and the expression for the force is given here. Chi is a susceptibility, H is the field produced by this magnet, and dH dz is the field gradient along the z axis. So, once again the system is calibrated with a known sample. We use manganese fluoride, which is a paramagnetic material. So, once you calibrate the system, any unknown sample, then you can mount it and do the measurement. Now, there is no need to shape this pole piece for the permanent, for the electromagnet to produce this gradient. Instead, in our system, there are coils which are called Lewis gradient coils. It is a solenoid where the number of turns per centimeter is changed. So, when you do that, there is a change in the magnetic field produced by the coils in the vertical direction that will produce the force. So, it is rather easy to do than shaping the pole pieces into a parabolic shape. That is rather difficult to do unless it has special machining to do to take care of that. Now, the alternating gradient magnetometer is similar to the Faraday balance. The Faraday balance, there is a gradient acting on the sample. That is a DC gradient. It is a gradient in the DC or permanent magnetic field. Whereas, in the AC gradient, there is a coil that would produce a gradient felt by the sample, which would change with time. So, this one would make it easy for detection of the magnetic moment, and so it is little bit more sensitive than the Faraday balance. But other than that, the only difference between the two is one is DC magnetic field gradient, the other is AC. So, all three are available from commercial system manufacturers, and most expensive one is the VSM, because it has the capability for low temperature measurements, and also you can have the sample parallel to the field or perpendicular to it. So, you can get the hysteresis loop in plane or out of plane. So, that will allow you to determine the anisotropy field and few other things. And the Faraday balance, you do not have the freedom to align the sample, because the sample always aligns along the easy direction. So, if it is the in plane is, if that is the easy direction, it will always align that way, and there is no way to turn the sample and to make it perpendicular, because it is a freely suspended sample on a thread or a wire, and you do not have the freedom to do it. The AC gradient is little bit better. You can reorient the sample the way you want if necessary. Right. Then the magnetic domains, in a ferromagnet, the sample splits into many regions in which the magnetic moment is aligned parallel to each other. These are called domains. Why would there be any domain formation? What is the reason for it? Okay. So, all the way left, this is a ferromagnet where the moment is all in one direction. So, if you look at the field lines will travel through the air surrounding the material, and that is not the state of minimum energy. Instead, the middle one shows this splitting into two different orientation, up and down. So, these are two domains, these are 180-degree domains, and this has little bit less magnetostatic energy compared to the previous one. But the third one is even much less magnetostatic energy. These are 90-degree domains. As you see here, the field lines are confined to the interior of the material, that is the minimum energy state. All systems in the universe, they will try to be in a state of minimum energy. You pick up something and let it drop, it drops because it has a potential energy. So, at the ground level it has 0 potential. So, that is what really happens. Any system, no matter what, it will always try to be in a state of minimum energy, and the domain formation is just because of that. And you can image the domains in either single crystal or polycrystalline material. There are many ways to do it. What you see here is the domain imaging by Kerr effect. Kerr effect is you shine light onto the sample surface, then you get the reflected light through a polarizer and an analyzer, depending on the grain orientation of the magnetization. So, there will be a small change in the polarization angle, and when you use the detection, the different grains will show up as a change in the contrast. So, these are grains of different orientation on the surface of some, I do not know what sample is this. So, that is how you do the grain imaging using magnetooptic Kerr effect. There are other ways to do it, and people used to do this bitter technique. What you do is you take Fe3O4, which is a ferrite, and just dissolve some of it in alcohol. Then you polish the sample pretty well, and then disperse this magnetic particle on top of it, and they will orient in the direction, because if there are domains, there is a domain wall separating 2 domains. So, there is a field gradient, because the magnetization, they are oriented in different direction in 2 neighboring domains. So, at the interface there is a gradient. So, all the magnetic particles will be attracted toward where the gradient is maximum. So, it will accumulate right at the domain boundary, and this is how you visualize the domains using the bitter technique. But there are much better ones now. The Faraday rotation imaging is similar to Kerr effect, but you look at the domains in the transmitted light. You allow light to go through your thin film sample, because the film has to be transparent for it to work. Then you look at the light transmitted with a polarizer. So, depending on the grain orientation, there will be a change in the angle of polarization, and that would show up as domain structure. And these are what are called 180-degree domains, and the sample has an anisotropy perpendicular to the plane. So, what you see as bright one is domains with magnetization up, the dark ones are domains with magnetization down. So, these are 180-degree domains that we saw earlier, and these are seen in the Faraday rotation imaging. And when this is usually Utrimer and Garnett, I am pretty sure. And if you have a small static magnetic field, you can easily visualize the change in the domain configuration. It is 4 Oersted, that is a very small field versus 0. Okay. And this one is magnetic force microscopy. You can image the domain structure in the MFM amplitude or phase image, and it's a traditional atomic force microscopy technique, but the probe is sensitive to magnetization. That is what shows up this domain structure. Right. You are familiar with hysteresis. What really happens is, for example, if you load your sample in a vibrating sample magnetometer and you start increasing the static magnetic field. So, initially when there is no field, the sample has domains with magnetic orientation in different direction. So, the net moment as a whole is 0. That is the reason if you bring two pieces of iron together, nothing really happens, because they are all split into domains. The net moment is 0 in the two pieces. Unless you apply a magnetic field, you would not realize that it is rather magnetic. So, when you apply a magnetic field, there are two things that happen. The domains in the direction of the magnetic field will grow at the expense of domains with opposite orientation, and also there is domain rotation. So, now the whole domain magnetization will rotate and will try to align in the field direction. So, it is domain wall motion where the domains grow and the domain rotation. These are the two mechanisms, and that is what really happens as you keep increasing the field. The magnetization increases until you reach saturation where all the domains are oriented in a particular direction, which is the direction of the field that is applied to it. Then you go back and the magnetization will decrease, but when you hit 0 field, it does not quite go to 0, because some of the domains are left with partial orientation parallel to each other. So, there is a non-zero magnetization when you go to 0 external field, and that is what is called the remnant magnetization. So, there is saturation magnetization when all the domains are aligned parallel, and then when you go back to 0 field, the leftover magnetic moment is called remnant magnetization. Then you reverse the field until you hit the coercive field, when the domains are reoriented in such a way that the net magnetization is 0. Then you keep going on the other direction, then it saturates, then you come back up. This process repeats. So, this is true for all ferromagnets, but it may have different characteristics. A permanent magnet like barium ferrite or strontium ferrite will have a very large remnant magnetization, whereas nickel ferrite may not have that high a remnant magnetization, and it will drop to close to 0. Now, these are two different cases. One is a soft magnetic material, it is a soft ferromagnet, and the coercive force or the coercive field or the field where you can make the magnetization to go to 0. That means when you want the remnant field to vanish, so the coercive force is very small, and that is the characteristic for soft ferromagnets, and it is true for iron, nickel, cobalt. Cobalt is a little bit hard, but iron, nickel, permandur, these are all soft. Nickel ferrite is soft magnetic material, and the hysteresis will look like this with a small Hc value. But barium ferrite, strontium ferrite, alnico, samarium cobalt alloy, they are all hard ferromagnetic materials, and they will have a very large coercive field. So, for a permanent magnet, you would like to have this kind of hysteresis loop, where the leftover magnetism under 0 external field is large enough so that it will behave like a magnet without having you to apply an external field. It is already magnetized, it keeps some of the magnetization, and that is what you realize with a permanent magnet. So, the permeability is essentially the slope of this M versus H at low field. So, the initial permeability is the magnetic induction over H. What is shown here is B versus H. B is equal to H plus 4 pi m, and so it's called magnetic induction, and mu m is at the knee of the magnetization curve. Okay. So, the maximum permeability is where this maximum in slope. So, that occurs somewhere in the middle point. So, the initial permeability is a key parameter. So, it tells you that whether the material has high affinity for an external magnetic field. When the permeability is very high, the field lines due to the external field, they are likely to go through the material rather than in air. So, you want high permeability materials for use in certain applications. So, what is magnetocrystalline anisotropy? Now, we just saw there are domains in a ferromagnet. So, when you apply an external magnetic field, there is rotation of the domains as well as there is also the domain wall motion. These two mechanisms will involve some energy. So, when the magnetic field is applied in different direction, it takes more for you to do the magnetization in a particular direction than some directions are easy. So, the easy directions behave as if there is an internal magnetic field present in the sample. That internal magnetic field is called magnetocrystalline anisotropy field. Why does it happen? Because you know that the magnetic moment essentially arises from two sources. One is the spin of the electron, the other is the motion of the electron in a circular path around the nucleus. So, that is orbital motion. And there is spin orbit coupling, because when the electron moves, there is interaction between the electron and the crystal lattice. The crystal lattice will produce an electric field. For example, in nickel ferrite, you have oxygen all around, right? It is negatively charged. So, it will produce an electric field. So, the electrons, they have a coupling to the lattice, which is called spin lattice coupling and spin orbit coupling, and those two sources will give rise to this inherent magnetic field, which will define an easy direction for the magnetization. So, it is as if there is an internal magnetic field present in the sample. That is magnetocrystalline anisotropy field. It can be small or large depending on the material. For example, some of the spinel ferrites like nickel ferrite, it is not very high, it is about 500 Oersted. But in barium ferrite or strontium ferrite, these are hexagonal structure and it can vary from 17 to 18 kilo Oersted. And if I substitute aluminum in barium ferrite, you can hit values as high as 40 kilo Oersted. So, barium and strontium ferrites, they are uniaxial, the field is along the C direction, but some of the hexagonal ferrites, they have easy plane. So, it does not matter, this is the C plane of the sample, any direction within the plane is easy direction. Okay? So, there is no preference. So, there are easy direction and easy plane anisotropy, and that is the source of magnetocrystalline anisotropy. And you have in the case of permanent magnets, the uniaxial anisotropy field that leads to the permanent magnetization, a large permanent magnetization that will make it like in the refrigerator you have the magnet. These are all made of barium or strontium ferrite dispersed in a flexible medium such as rubber. You have the lining with barium ferrite and it will attract, and then the fridge door will close properly for you to keep everything cold inside. And magnetostriction is also related to the motion of the domains under a magnetic field. So, as we know, when you apply an external magnetic field, these domains will either rotate or move toward, grow with maximum volume toward the field direction. So, these would involve a shape change in the bulk of the material. So, some mechanical strain. That strain is what we call magnetostriction, and the strain will increase as you increase the external magnetic field, and ultimately it will reach its saturation value. This is the magnetostriction versus static magnetic field for iron and nickel. It's the iron at low field it is positive, it goes through 0 and then it's negative. It's nickel, it's negative all the way, but ultimately they all reach saturation. Okay. So, cobalt it has positive magnetostriction, nickel has negative, permanganate has positive, and lead glass that we saw earlier it has positive magnetostriction. So, there is nothing unique about whether it can be positive or negative, it could be either one depending on the nature of the material, but the driving mechanism is the rotation and expansion of the domain in the ferromagnet under an external magnetic field. So, you can measure the magnetostriction using several different techniques. You can use optical interferometry, strain gauges, that is what we use, and also you can use piezoelectric transducers or some resonant techniques to measure these. For our interest, most of the ferromagnetic materials, you can measure the magnetostriction with a strain gauge and a strain indicator. This is the easiest method instead of using something fancy like optical interferometry. Okay. And we know about this, I showed this earlier, this is the strain gauge, it forms a Wheatstone bridge. So, the bridge output goes to the strain indicator, and whenever there is strain, the resistance of this arm will change. So, leading to a condition away from balance. The strain indicator will correct for that and will produce an output which will show the strain in parts per million. Okay. So, you can directly read what the strain is, and it can be measured parallel to the magnetic field or perpendicular to it, it does not matter. You put the strain gauge on the sample. For parallel for magnetostriction, you apply the field along the strain gauge direction. For perpendicular, you just apply perpendicularity, that is all. You can also do lambda 1 1, 1 2 and 1 3. Okay. All right, let us go on to the next one that we are interested in. The other phase that we use in most of the composites, it is either ferroelectric or piezoelectric. In a ferroelectric, similar to a ferromagnet, in the ferromagnet there is spontaneous magnetization. In a ferroelectric, you have spontaneous electric polarization, and that can only be reversed if you apply an electric field, similar to the case of a ferromagnet, where you cannot reverse the magnetization direction unless you apply an external magnetic field, and it takes energy to either reverse the polarization or realign the ferroelectric domains in the ferroelectric. And piezoelectrics, they are not ferroelectrics. Most all materials are piezoelectric in the sense that if you apply an external electric field, there will be mechanical deformation, like such as quartz or aluminum nitride. These are not ferroelectrics, but they are all piezoelectrics, because there is always a change in the charge configuration that will lead to a dipole moment under only external electric field. And this is the traditional hysteresis loop associated with a ferroelectric. D is the displacement, and it is sum of 4 pi e plus the polarization. It's very similar to what you have for ferromagnets, B versus H. This is D versus E. So, you can polarize the ferroelectric, it's okay, but there is always their resistivity is not infinite, it's finite. So, you have accumulation of charge, positive charge on one end, negative charge on the other end, when all the dipoles are oriented in a particular direction. And there is always a force of attraction between positive and negative charges. So, there is always a current, it is a leakage current. So, ultimately if you do not do anything, if you remove the external electric field, the leakage current will cancel out all the charges, you will end up with zero polarization. Okay. So, some of the examples for ferroelectrics are PZT, barium titanate, and PM and PT, these are called relaxer ferroelectrics, and barium titanate and PZT are traditional ferroelectrics. So, the transition from ferroelectric to paraelectric state is very sharp in PZT and barium titanate, whereas in PM and PT, if you look at the polarization versus electric field as a function of temperature, it is rather very shallow. So, it occurs over a wide temperature range and it is not very sharp. So, that is the signature for relaxer ferroelectrics. And this one shows traditional ferroelectrics such as barium titanate or PZT for temperatures above the ferroelectric Curie temperature. The structure is rather cubic, and the titanium or zirconium, they are all placed right at the center of this octahedron. So, the center of positive and negative charges, they overlap. The negative charge here is oxygen, the positive charge is either titanium or zirconium. So, when there is no separation between the center of positive and negative charges, the polarization is 0. But once you go below the Curie temperature, there is a slight displacement of the central ion, and so the center of positive and negative charges do not overlap any longer. So, there is a net accumulation of positive and negative charges separated by a small distance. So, there is net polarization, and this small polarization is the one that is responsible for the spontaneous polarization and the ferroelectric order. This is true for barium titanate as well. And these are typical polarization versus electric field for PZT at a series of increasing temperatures, and this one is the saturation polarization, and what you see here is the remnant polarization, and that keeps decreasing as you increase the temperature, and it will just vanish when you hit the ferroelectric Curie temperature. And this is the strain or D33 versus the electric field, once again for I believe these 975, maybe these are all the centering temperature when they made these PCT. So, when you make PCT, you have to be extremely careful, because lead has a tendency to evaporate and escape from PCT. So, in order to avoid any loss of lead that you need in the PCT, you always disperse some lead around it. So, that will compensate for any loss, and then you can get stoichiometric PCT if you make it. But we always buy PCT from vendors. It is not that expensive. You get them pre-poled with silver electrodes already deposited on PCT. They use silver paint, to make those electrodes on top and bottom. So we buy the platelets already pre-poured, and they are good enough. You can quickly make a composite and do whatever you want. So there are, depending on what exactly you want, you can substitute different ions into PCT and make either, soft PCT or hard PCT. Soft PCTs are defined by a very high dielectric constant, a high D33, and rather small Curie temperature, whereas hard PCTs have much lower dielectric constant and smaller D33, but they have higher Curie temperature. Depending on the application, you may use either soft or hard PCTs. These are the ones that people, the companies made for applications in Navy. They use underwater transducers and other communication devices, and most of them use different types of PCTs depending on what exactly the application is. So in our case, we use soft PCTs because you want high D33 to achieve a large magnetoelectric response. So we stay away from hard PCTs, and soft ones are the ones that we use. And barium titanate, it's similar to what I just talked about on PCT. So the structure is cubic above Curie temperature. Below Curie temperature, it has a distorted structure. Barium ions are displaced from the center, leading to a polarization. P versus E will look like this. It's similar to what you have for PCT. And the strain is always either positive or negative. It doesn't switch sign when you reverse the electric field. So these are electrorestrictive, and that is what you have for barium titanate. And PM and PT also the same way. These are relaxer ferroelectrics, and they have very high electrorestriction. D33 may be on the order of several thousand. For PCT, it's anywhere from 400 to 700 for the soft ones. Barium titanate is even smaller, whereas with PM and PT, you can get D33 as high as 2 to 3,000 in PM and PT and PC and PT. And the mechanism for the ferroelectricity is rather not completely understood, and these are relaxer ferroelectrics, and they are characterized by a slow change from ferroelectric to paraelectric state. So it's spread over, the transition is spread over a large temperature range. That's not the case for PCT or barium titanate. And there are series of relaxer ferroelectrics, PMN, PM and PT, PLZT, and PZN, PT, and several combinations. And so you can differentiate all of them from the polarization versus electric field. This is just a piezoelectric, and that's P versus E is linear. So when you go to a ferroelectric, so that is shown in B, where this is the characteristic that you see for PCT or barium titanate, and where there is saturation of the polarization, then you go back to zero electric field, there is remnant polarization. The third one is what's called antiferroelectric. So the moments are, the polarization vectors are antiparallel to each other, and you don't have to worry much about it. We don't come across this. Lead titanate is antiferroelectric, for example. And finally, for relaxer ferroelectric, it's characterized by a thin P versus E, whereas this one is spread out, and the remnant polarization is rather small compared to traditional ferroelectrics. This is PM and PT, and so depending on the amount of lead titanate in PMN, it has very different characteristics, and these are shown here 28% PT and 37% PT. As you see here, we use most of in our systems, we use PT of 36 or 38. It has a much higher D33 among all the compositions available for PM and PT. So, how do you measure? We have a ferroelectric tester made by a company called Radiant Technologies, and it has a holder, that is what is shown underneath. You can get P versus E, and also you can measure D33 versus E, and so on. The middle one is a quick and dirty way of measuring D33. It is a simple setup. There is an external sample holder, or the one we use, it is an older model. The sample goes on top with a mechanical vibrator. It will vibrate on the sample surface, and then that will produce a voltage. The unit measures that voltage, and it is converted to D33 in the unit of picometers per volts. And also you can measure, with a traditional LCR meter, the capacitance across PCT. So, that way you can measure what the dielectric constant is. And these we have already seen in many of the earlier talks. So, measuring the magnetoelectric effects, we had demos in the tutorials on all these things. So, right. So, I will wrap up this section with, I just talked about ferromagnetism and ferroelectricity, and we went through different phenomena associated with both kinds of materials. One, there is ordering of magnetic moments. The other, there is spontaneous ordering of electric polarization, and there is always a mechanical force associated with both, either in a magnetic field, which is magnetostriction, or an electric field, which is the piezoelectric effect. And then we know how to put these two phases together to make it a magnetoelectric composite, and we know what to do with how to measure the overall magnetoelectric coupling by different means, either the effect of an external magnetic field or an electric field. Okay. Right. So, let me take any questions, then we will go on to the next topic. Yeah, sure, I can. Right. The next talk is on applications of multiferroic nanostructures. You can do research all day. At the end, it has to have some benefit for the society. And that's what the applications are all about. So I will talk about antenna miniaturization. Then NEMS is nano electromechanical systems. MEMS is micro electromechanical systems. So these are going to be either on miniaturized antenna or magnetic sensors. So the magnetic sensors is something very important, and so I will spend time on all these applications. So the antenna miniaturization I will talk about using a ferrite ferroelectric bulk composite. This has nothing to do with the magnetoelectric effect. I'll just you'll see that in a minute. Then there are layered composites which are NEMS or MEMS. It is for true miniaturization for antennas from hundreds of megahertz all the way up to several gigahertz. And then we'll look at picotesla magnetic sensors, and then how to miniaturize them. So you come across antennas in every applications, both civilian and defense oriented applications. For civilian applications, the cell phone that you use every day and every minute, it has an antenna. It has to receive signal and also it has to transmit signals. And also you have the TV, radio, and GPS. And in the car, there is, if you have collision avoidance radar, that has an antenna too. So for defense-oriented application, you have the unmanned aerial vehicles, all the drones they are using to kill each other in Ukraine. That has an antenna, and it receives the signal from GPS. And also soldier communication. There are antennas where it is stitched to their uniform, so it's miniaturized and easy for them to carry around. And also you have antennas in the ground vehicles like tanks or Humvees. So it's pretty much everywhere, and the need for antenna miniaturization is, for example, in the defense oriented application, if the soldier carries a huge antenna around, it's extra weight, and also he cannot hide his presence. Everything sticks out, right? He becomes an easy target. So you would rather have the person wear something, a wearable antenna which is miniaturized. And same way with your cell phone, you don't want to carry around a huge cell phone like as big as a radio. And so miniaturization is a key for all the applications. So how do you miniaturize an antenna? So the first thing I want to discuss is how you can do it with a bulk composite of a ferrite and a ferroelectric. For this particular example, I used a 100 megahertz antenna. This project, 2 high school students, they did in my lab, and this is what they did, and that's what I'm going to describe. And so they did the miniaturization of 100 megahertz antenna. So in free space, if you don't do any miniaturization, for 100 megahertz, the wavelength is 3 meters. These are dipole antennas, and the overall length is 1/2 of the wavelength, which is 150 centimeter. So you form a standing wave in the antenna. So you store energy, it will radiate energy, or the receiving antenna, if there are waves that will match the resonance condition for that, it will receive and then So it can do both, transmit as well as receive. Now how do you shrink the length of the antenna from 150 centimeter to smaller value? The only way you can do that is, the wavelength is fixed in air, 150 centimeter, but you can shrink the wave in a medium. This medium that we are going to build is a composite of a ferrite and a ferroelectric. And how do you shrink the wave? If the wavelength in air is lambda and if the index of refraction is n, then the wavelength inside the material is lambda in air divided by the index of refraction. The index of refraction is square root of the product of the relative permeability and relative permittivity. That is fine, you can do it. Also, you have to make sure that the antenna has impedance match to free space. If it does not have it, then most of it will, radiation will be reflected back to it. So, impedance match will allow for the radiation to be very effective. And what is the condition for that? If the impedance of the free space is Z naught, then if you make mu r and epsilon r equal in magnitude, then the impedance of the medium will be equal to the impedance of free space. The free space impedance is close to 150 ohms. Okay, so just to let you know. So, what we did was, or what the students did was to choose a ferrite and a ferroelectric. Now, the idea is to make mu r and epsilon r as high as possible, but also mu r equal to epsilon r for impedance matching. So, they chose nickel zinc ferrite for high permeability, and for ferroelectric phase they used bismuth strontium titanate. And these are the two materials they chose, and for the ferromagnetic phase they chose this composition nickel 0.8, zinc 0.2, Fe2O4. So, it is nickel zinc ferrite with 20% zinc. What is shown here on the left is mu prime and mu double prime as a function of frequency, and you want to make sure that the value of mu prime is high at 100 megahertz. That is the whole idea, because the miniaturization is at 100 megahertz, and also you want mu double prime to be as small as possible, because that is a measure of loss, the magnetic loss in the medium. The same way in bismuth strontium titanate, you can get high permittivity and low loss. So, these are the two choices, but mu prime is around 20 at 100 megahertz, and epsilon prime is 350 at the same frequency. But we want mu r and epsilon r to be equal. So, that would mean that you cannot mix these two in 50-50. You can have a composite of nickel zinc ferrite with a small amount of bismuth strontium titanate. So, we just added 2% BST to the ferrite powder, then it was sintered, and this is what you get when for the sintered composite. Mu prime is close to 15 and epsilon prime is close to 20, and mu double prime is very small at 10 power 8, and so does epsilon double prime. So, it has low losses, both magnetic and dielectric loss, and the mu prime and mu double prime are pretty much in the same range. For you want impedance matching to free space, you can get it. Okay, so, these are the sintered composite they prepared. So, this one is a 5-inch substrate, and the antenna is just a copper strip with an input and an output as shown here. And this one S11 versus frequency, it shows where the antenna is effective. You see the resonance at 100 megahertz. So, this is a 100 megahertz antenna which can either transmit or absorb microwave power at this frequency, and it would be pretty easy for you to miniaturize. So, you went from 150 centimeter to the length here is close to 10 centimeter. So, that is miniaturization. Okay. That is one thing. Okay. So, but still it is very high. You do not want a cell phone with 15 centimeter long antenna, right. You want ultra miniaturization. The question is, how do you accomplish that? That is where the composite comes into use. So, the ultra miniaturization can be done with a composite of a ferroelectric and a ferromagnet, or a piezoelectric and a ferromagnet. How it can be done? You have to drive the composite to resonance condition. As shown here, we know that the voltage coefficient peaks at resonance. It can be bending resonance or longitudinal resonance. So, if you can reach that condition, then the antenna can be miniaturized. So, how does it function as an antenna? So, let us see here, this is the transmitting mode. It is just a composite of a ferromagnet and a piezoelectric. So, you apply an AC current or voltage to the piezoelectric layer. Okay? Then what does it do? It will produce piezoelectric strain in this medium. That strain will be transmitted to the magnetostrictive medium. So, it will induce a change in the magnetic property in the like it can be either magnetization or a change in the magnetic anisotropy, but the input is an AC electric signal. The output here is an AC magnetic radiation. So, it will radiate in the form of magnetic waves, that becomes an antenna. So, it becomes a transmitting antenna. Then for receiving antenna, how does it work? So, when it receives radio frequency signals, it is in the form of a voltage that is applied to the magnetic medium. So, all the radiation, if you are familiar with electromagnetic waves, it has both electric and magnetic component to it, right. They are perpendicular to each other. So, the incoming radiation will have a small AC magnetic field in the RF signal that would produce strain in the this medium, which will be transmitted to the piezoelectric medium, that will produce a voltage. So, this is the receiving end, and the transmission is also that is what I just described. So, you can do ultra miniaturization with a composite of a ferromagnet and a piezoelectric. What kind of miniaturization? It is pretty much your imagination, because you can control the resonance frequency of this. We know that the resonance frequency depends on the dimension, correct. So, you want to operate this under resonance condition. It can be bending resonance, or it can be longitudinal or radial acoustic mode, and this would happen at kilohertz, hundreds of kilohertz, if the sample is 2 centimeter long. But for ultra miniaturization, you can make it as small as possible, just a few tenths of a micron. So, smaller the dimension, higher the frequency. So, you have a miniaturized antenna that can be used at 100 megahertz or several gigahertz. How do you go from megahertz to gigahertz? It is easy, because you do not have to operate always at longitudinal or resonance or radial mode. You can create standing waves in the thickness. So, the thickness being small, the resonance frequency will be in tens of gigahertz. So, you can miniaturize several frequencies, like anywhere from a few hundred megahertz all the up to tens of gigahertz by choosing the dimension, either the lateral dimension or the thickness of the composite. So, that is the key. So, this is a nano electromechanical system. It is a miniaturized magnetoelectric antenna, and what you see here is a scanning electron microscope image of the antenna operating at very high VHF or ultra high frequency UHF. VHF is some of the letters are left out. This is 2.53 gigahertz and this is 60 megahertz. And as you see here, this is an antenna consisting of two elements. One is ferromagnetic, the other is ferroelectric. I believe this is aluminum nitride for the piezoelectric phase, and it is iron boron type compound for the ferromagnet. It is there in the next slide. Unfortunately, it is missing, but I am pretty sure it is iron, boron and aluminum nitride. Okay. All right. So, this is the characteristic for the this an antenna operating at 61 megahertz, and that is the picture. Yeah, it is right here, aluminum nitride and iron gallium boron. So, it's the dimension is quite small. The scale here is 20 micron. So, this may be just less than 200 micron in length, maybe 100 micron in width, and much smaller thickness. You do not worry about that part. And what is shown here is the this is where the voltage coefficient, magnetoelectric voltage coefficient, it peaks at the mechanical resonance. In this case, it is lateral acoustic mode, and the frequency of this is about 61 megahertz. That is what happens when you shrink the length from several millimeters to hundreds of micrometers, and the resonance has very high Q. That is what you want a frequency selective antenna to be. If the Q is very poor, then the antenna selectivity for frequency is very poor. Okay? It is spread out. This resonance will look rather wide, and so the frequency selectivity becomes rather poor. Right? So, at resonance, the voltage coefficient, you look at the value, it is 6 kilovolt per centimeter Ørsted. It is not even volt, it is several kilovolts, and it makes it an excellent miniaturized antenna operating at this frequency, and there is not even a bias magnetic field applied to this. But if you apply a bias magnetic field, it will be even better than what you see here. Okay. So, the strong ME coupling, it leads to very high electromechanical transduction. So, it is a very good receiving and propagating antenna, and the frequency is RF range, and the Q value is also quite high. It is a very well efficient frequency selective antenna, and so in the previous case with the composite, what we had for 100 megahertz was a length of 10 centimeters or 15 centimeters, right? Here just a few hundred micron, and it is pretty good miniaturization. Okay, so the question is, how do you go from few hundred megahertz to several gigahertz? Okay, I told you that instead of choosing the resonance which is associated with the length or the radius, you go for the resonance associated with the thickness. That is what this F bar antenna does. It is a disc of a composite with two faces and it's iron gallium boron and aluminum nitride. There are gold electrodes top and bottom, and you drive this into a resonance mode, a standing wave confined to the thickness of this, and that happens at 2.53 gigahertz. So, it is a 2.53 gigahertz antenna, and the resonance is pretty sharp with a Q value of in excess of 600, and so this is, they call it F bar antenna. We did not do it, but our collaborators at Northeastern University in Boston, they are able to demonstrate this miniaturization. Okay, these are some equations, just ignore it. So, the key is depending on the frequency, you can choose the lateral mode or the radial mode in a composite to put together antennas in hundreds of megahertz. And if you want to go further in frequency, just choose the proper thickness, you have miniaturization in the gigahertz range. Okay. So, the previous one, this is NEMS, this is MEMS, and this one is NEMS. Okay. So, these are the two different kinds, and you have the antenna. So, let us move on to magnetic sensors. There are several types of magnetic sensors, and squid magnetometer, it costs thousands of dollars, and it does not consume that much power, but each sensor element is more than $10,000 depending on the application. For example, if you want to put together a system for magnetoencephalography, where you want to record the magnetic field produced in a human brain, then you need several of them. The unit is very huge, and it is also very expensive, and people most of them cannot afford to have that procedure done unless they are super rich or the insurance company would pay for it, right. And there are other options. You can put together a sensor array with magnetoelectric composites. They are very cheap, and also it does not consume too much energy. You can make an element for less than $1, and also it has a large bandwidth. So, there are other techniques for measuring the magnetic field: surge coil, flux gate, giant magnetoresistive sensors, and the Hall effect sensors. So, what is so unique about these sensors? For the defense oriented applications, if you want to see behind the wall, if there are enemies carrying guns and running around, so the sensor mounted onto the soldier's head, it is sensitive to magnetic field, and then the sensor electronics could convert the magnetic signature into an image. That is one option. Then the roadside bombs, it cannot detect chemicals which are the key ingredient in the bomb, but if some terrorist would dig out the roadside, put a bomb in it, then as the sensor scans the roadside, it can identify some anomaly. There is something missing. A traditional road which has a lot of iron and other impurities, it will look much different than a pit where a bomb is hidden. So, from the anomaly you can detect the bomb, and there are other things such as magnetic signature will provide key information regarding what is going on in the defense related applications. And for civilian applications, you have as I just mentioned, biomedical imaging and other applications. And so, how do you detect a magnetic field with our magnetoelectric sensors. You have to detect either both AC and DC, correct? So, for measuring the AC magnetic field, you can put together a composite and then measure the magnetoelectric voltage coefficient under a DC magnetic field. So, this coefficient is measured as a function of AC magnetic field amplitude. So, you have a calibration curve. Any unknown field, you should be able to measure it. But the only drawback here is, you need a bias magnetic field, and I am going to talk about several systems that have self bias. So, you do not need an external source of magnetic field, that can be taken care of. Now, the other, so this is okay, because for 1 arstir of AC field, you may generate a few hundred millivolts of signal. So, the detection is rather very limited, because the signal you are getting from the sensor is only millivolts, correct. So, the question is, how do you increase the sensitivity? The answer is, use the resonance mode to your advantage. How is it done? You always have a driving field which will drive this composite into longitudinal resonance at a few hundred kilohertz, for example. Then you superimpose the field that you want to measure. So, the field that you want to measure, let us say that frequency is f, the resonance is occurring at f naught, then the field that you want to measure will appear as two peaks around the center one at f naught plus f and f naught minus f. Then you measure this amplitude, that is rather high, it will be several volts or hundreds of volts. So, you can enhance the sensitivity of the system by operating the sensor under resonance condition. Then what about measuring the DC magnetic field? We use what is called delta E effect, and it is well known effect, and if you are not familiar with it, you can look up Wikipedia or any textbook. And what it is so if you apply a magnetic field to a system under mechanical resonance, then the DC magnetic field will produce a change in the Young's modulus that will show up as a small shift in the resonance frequency. So, depending on the shift, you can calibrate the system and you can measure the DC magnetic field. That is what is shown here. So, the delta E effect is change in the Young's modulus and the change in the resonance frequency. In this case, you can drive this into longitudinal or thickness mode in the resonance, then apply a DC magnetic field, then measure the shift in the frequency, then you have a sensor of DC magnetic field. And this one is a miniaturized micrometer scale sensor capable of measuring a DC field. So, there are by now what you can select for a magnetic sensor for the ferromagnetic phase and the piezoelectric phase. You can choose nickel, permanent med glass, they have pretty good magnetostriction, and most of the our collaborators, they used iron gallium boron, that is pretty good too. On the piezoelectric side, you can use a ferroelectric such as PCT, PMNPT, or a pure piezoelectric such as aluminum nitride or quartz for the thing. And these are the traditional ferromagnets. We are familiar with all these variation in the magnetostriction as a function of bias magnetic field. Nickel has negative magnetostriction, permanent has positive magnetostriction, and med glass also has positive magnetostriction. And the bottom curves here, it shows the piezomagnetic coefficient versus static field, and this one is for med glass. Okay, so how do you put together a magnetic sensor? The sensor you want to make should be capable of measuring picotesla for magnetocardiography or femtotesla for encephalography. These are 10 power minus 12 and 10 power minus 15 Tesla. It's not easy. These sensors are to be ultra sensitive to AC magnetic fields. And the only way to make them so sensitive is to screen the Earth's magnetic field. The Earth's magnetic field is 0.4 Ørsted or 0.4 Gauss, and that's big enough to wipe out any signal that you measure with the sensor element if the signal that you measure is picotesla or femtotesla. So, most of the MCG and the magnetoencephalography systems in a hospital, they have completely shielded rooms. These walls will be shielded with high permeability material like mu metal, and it has permeability of several thousand. So, it will take care of Earth's magnetic field, it will shield it completely. The magnetic field lines due to Earth's field will be excluded from this room. It will be confined into the shielding material itself. So, in our system we used a 3-layer of the sensor is enclosed inside a shield. The shield is made of 3 layers of mu metal. These are cylinders made of mu metal, thick mu metal, and that is what is shown here. So, the sensor itself is mounted on this plexiglass holder. There is a barium ferrite if you want to produce a bias magnetic field, that is a permanent magnet. So, the sensor element is inserted here, and then the whole thing is shielded magnetically. And also we wanted to provide acoustic shielding. In the building, people walking around, all those things, that will produce a pickup in the noise signal. That can be avoided by enclosing the whole thing in styrofoam, styrofoam. So, you can build an enclosure out of styrofoam, that is an acoustic shield. Then you have to shield any RF radiation. There are so many waves like radio waves, the TV stations coming in, it's propagating in air, right? And your sensor can pick up those signals. So, to avoid that, there is RF shielding, that is not shown here. These are carbon cubes all around the sensor element that will absorb anything that is RF. So, when you do all these things, what you do is, to begin with, this is the a tri-layer of nickel, PCT nickel, for example, and this one, this sensor element operates at low frequency, there is no resonance, and this is the mu voltage coefficient as a function of bias field. Now, what is shown here underneath is the noise signal. There is no AC field applied to the sensor element. So, we used the output of the sensor element is fed into a spectrum analyzer and a preamplifier. The field that we generate to look at the sensitivity of the sensor element, it is a nanoampere Keithley current source, and that will produce the current that you want to measure. There is a solenoid that the current is passed through the solenoid. It's nanoamperes of current which will produce picotesla magnetic field. So, that is how we characterize the sensors, how sensitive it is, what is the lowest field it can measure. So, how do you find the lowest field it can measure? The only way to do that is, do not apply an AC magnetic field, just measure any signal that is present across the PCT in the sensor element and feed that into the spectrum analyzer. So, the spectrum analyzer shows the voltage as a function of frequency. As you see here, as the frequency increases, overall this thing goes down. This one would put a limit on the lowest field that can be measured, because this is present without any field present, applied to the sensor element, correct? So, we have to convert this into magnetic noise. So, that is, you have to, there is a formula to find the magnetic noise. That is this formula, magnetic noise. So, I do not want to confuse you with too many details. So, V root mean square is V RMS divided by what is S? It is the transfer function, that is the sensitivity of the composite, how much signal it will produce for a given voltage V over the, how much signal it will produce for a given applied field. So, the field is in Tesla and then square root of frequency. So, these are the noise data for different types of sensors, and as you see here, we put together whole series of sensors, and some of them have permandur and PCT in it, and I can't see. Okay, that is permandur PCT, nickel PCT and nickel zinc ferrite PCT. And what we did was, we made a long tri-layer of PCT with permandur on top and bottom, right. What you can do is, the long PCT, you can divide that into 5 different elements. How? The PCT surface has silver on it, right. You etch the silver at periodic intervals, then connect them in series. It becomes a 1D array containing 5 sensor elements. Okay. So, that gave us the lowest magnetic noise. So, you can go from this is nickel PCT nickel, the noise level is 150 picotesla per root hertz. That would mean that the field that you want to measure should be at least twice the noise level. So, it is good only for fields equal to or above 300 picotesla, that is what it means. So, now if you want to use it for magnetocardiography, the signal that is produced is 20 picotesla, and it is sensitive, it is not sensitive for 20 picotesla, it is only 300 or above that value, it is no good. So, the only way you can do that is to keep looking at different options for the piezoelectric and the ferromagnetic phase, and we found that when you split this into 5 elements by simple manipulation, the noise will go down quite a bit, all the way to this is 75 picotesla per root hertz, and that is at if it is not driven into resonance. When you drive that into resonance, it is even much better. It can go down all the way down to 1 femtotesla per root hertz. So, if you operate it at resonance, and this is what you need for magnetoencephalography, that is to measure the field produced in the human brain. Okay, look at this number. It is, if it is not driven into resonance condition, the minimum is, the noise level is at 75 picotesla, but if it is driven into resonance, it is less than 1 femtotesla, and that is what we need for some of the applications. So, then there are other things that you can do by functionally grading the signal. If you grade the ferromagnet or the ferroelectric, what you can do is you can get rid of the need for a biased magnetic field, right. To operate the sensor at its best sensitivity, we know that you may have to apply a bias field that will produce a lot of difficulties when you want to put together an array, because each element will have its own magnet. There are too many magnets in the array, which will make it not suitable for doing any imaging. So, instead what you want to do is you want to have self-biased sensor elements, and that can be done with different techniques. And one of them is, if you grade the ferromagnetic layer. What do you mean by grading? Instead of using a single ferromagnet, homogeneous ferromagnet, you can manipulate the ferromagnetic layer with the choice of two different ferromagnetic materials. How does it help? We know that when you have a ferromagnet, you go up in magnetic field, the static magnetic field, then you come back to zero field, there is remnant magnetization, correct? So, if I have two different layers, one has a large remnant magnetization that will act on the second layer, and it will orient some of the magnetic moments in the second layer. So, you have a built-in magnetic field in the ferromagnetic phase. That is what you need for a biased magnetic field, right. So, the bias field can be produced by grading the ferromagnetic layer, and that is what we were able to do, and have a standalone sensor that does not need an external magnetic field to operate. So, that is what you see here. This one has mid glass and nickel. So, one layer of mid glass comes in the form of ribbons. So, it is just we used 1 to 5 layers of 25 micron thick mid glass, and this is nickel. So, this is graded by using nickel and mid glass, and it has PZT for piezoelectric layer, and this is the voltage coefficient versus DC field. And look at this value here. It has a non-zero voltage coefficient, which is rather good. It is close to 1 volt per centimeter Ørsted. So, this can behave as a self-biased sensor element. That is the whole idea. So, and under this condition, this is what we found. We applied nanotesla AC magnetic field and measured the output voltage across PCT, and it is rather linear. So, that is what you need for a magnetic sensor. It has to produce a linear voltage output, which is proportional to the strength of the magnetic field. And these 5 different curves are for different number of mid glass layers, 1 to 5, and it is pretty good sensor element. And this is the case when it is operated not at resonance, but at low frequency at 1 hertz. Okay. Now, this is the case at resonance, where there are 2 AC magnetic fields, one that drives the sensor element to resonance, and in this case it is bending resonance occurring at 130 hertz. Then on top of that is superimpose the signal that you want to measure, the magnetic field that you want to measure, and that appears as sideband, and it has a much higher sensitivity because it is operating at resonance, and you can use it to measure very small AC magnetic fields. So, these are the noise level at 0 external bias when the sensor operates at bending resonance. It varies from anywhere from like 80 to 120 picotesla per root hertz. So, any signal you want to measure must be 2 times in magnitude compared to the noise level. And this one, these are 2 different, one has PCT nickel mid glass and the other one has a layer of mud glass in contact with PZT, and then there is nickel. Then we also tried loading the bilayer with a tip mass. By loading it with an external mass, you can decrease the resonance frequency for bending all the way from 120 hertz to close to 5 hertz by using different tip mass, and that also helped to decrease the overall magnetic noise. Look at these values. It's a dramatic drop in the magnetic noise as a function of frequency, right? So, that is another way where you can have a self-biased sensor operating under bending mode, and also it has pretty good sensitivity for any applications. Then how do you miniaturize them? I have a collaborator in the electrical engineering. He came up with a process. It's more like traditional MEMS processing, and you go through series of steps. The tip mass here is one at the end of the cantilever. That's the proof mass. There are electrodes below and above the composite. The composite is made of lanthanum LGT, and also an ME element which can be aluminum nitride or quartz. So, this is what he came up with, and this is another collaborator. They made this DC magnetic field sensor. This is based on the delta E effect. It has iron, boron, gallium, and aluminum nitride bilayer, and these are the cross section for the bilayer stack. There is 50 nanometer platinum, then this is the aluminum nitride, and this is the iron, gallium, boron stack, and it has its own resonance. Then you superimpose the DC field that you want to measure, and then you have a shift in the resonance frequency, and depending on the DC field, the shift will change. But these are pretty, this one is operating under resonance in the thickness mode. Look at these frequencies. These are in hundreds of megahertz. So, as you increase the DC field, there is a shift, and then you do the calibration. It has very high Q, and it will be very sensitive to DC field. Right, to conclude, we talked about miniaturizing antennas with a ferromagnetic ferroelectric composite, then how to do ultra miniaturization with the use of a magnetoelectric composite for both AC and DC magnetic fields, and also I came up with some scheme to make the sensor self-biased with the use of graded ferromagnetic layers, and then how to miniaturize all the sensors or the antennas. So, that takes care of this part. Right? So, any questions? Okay, I think you have enough expertise now to go out and make a little small sensor out of a composite. And the only way to keep up with the field is look at latest publications. And there are journals devoted to sensors. There is IEEE sensors, and there are other bunch of journals. And the magnetic sensors based on composites, it's still an active field, and people are working and they are reporting latest work, and that's something you want to take a look at it, and if you are truly interested in this field. Okay. And also, of course, the antenna, they are also very important, not only just the sensors. And then you can catch up with the latest developments. There are IEEE journals for antennas and sensors. They are the very best source. Of course, there are hundreds of other journals, and I would suggest that you go on Google Scholar, scholar.google.com. All you need to do is just type in some search terms. You can type in miniature antennas or magnetoelectric sensors, and it will come up with hundreds of papers. Okay. All right, yeah, thank you. So in the afternoon, it's only tutorial. It's done for you.